Thank you for joining us on this journey to discover more about the English Riviera UNESCO Global Geopark, one of Earth's extraordinary places. In this series of interviews, our patron, Professor Iain Stewart, explores what it is that makes this geopark so special, from when the rocks around us were formed, to evidence of early humans, and right up to artists and writers who are being inspired by the geopark today.
So welcome to the latest in the Geopark in Focus webcast, where we're looking at different aspects of the English Riviera UNESCO Global Geopark. And one of the aspects we're looking at today is climate change. So climate change is something we have about all the time. It's on the streets, it's in newspapers. It's been pushed off by the COVID crisis, but it's sitting there, and it's an ever-present part of the contemporary scene. But today we're going to be looking at it from that geological perspective, because the geopark has got lots of evidence of past climate change. So we're going to be tracking some of that through, and then looking at the contemporary, what it means today. And with us as our guides today, our geo guides, are two luminaries of the local geological scene. We've got Dr Jenny Bennett, who's chair of the Devonshire Association's Geology section, and a specialist in Ice Age environment, the Ice Age landscapes, Ice Age context really. And then we've got Professor Malcolm Hart, who is Emeritus Professor at the University of Plymouth and is a micropaleontologist, but he's quite tall actually. So he's not especially micro, but he's interested in fauna, in kind of paleofauna, fossil fauna, and what they tell us about climate and oceans through time. So those are going to be our guides. And to crack on, I thought I'd start with you, Malcolm, because we've got a previous webcast from Mike Benton and Kevin Page that have set the scene, the early climate scene for the UK and southern Britain, really, in terms of the kind of Devonian period after which the area is named. But as we go into that Devonian, we go into this very dry period, the red rocks that are so characteristic of the southwest. Do you want to pick that up? Tell us about those red rocks, and then kind of what happens as we leave the red rock country and kind of climate.
I think when we look at the Devonian or the red rocks, what we really have to get over is that climate change is not just a modern phenomenon, and very often people present it as if it's a new problem, which of course it isn't. And if you go back just a little bit beyond the Devonian, we're fairly certain that the atmosphere, which was generated by volcanic degassing, was probably stabilized in terms of its chemistry by that time. And the same is true for the water on the planet. And therefore, what we're doing through that interval from the Devonian onwards is looking at how the atmosphere has changed. And one of the most important things that was brought out by Mike Benton in particular within the Devonian was the fact that it is the animal life and the plant life which is changing the atmosphere. And that's important because until we had vegetation on the planet, which really got going okay in the Silurian, but particularly in the Devonian, until we had that vegetation, carbon dioxide that we talk about all the time now was building up. And in the Devonian, carbon dioxide levels were very high. Mm-hmm. And therefore it really was perhaps not a greenhouse Earth. We know a bit more now about it, but certainly it's only when the plants got going that that carbon dioxide atmosphere began to reduce. And of course it was later, and we'll come on to that, that once the ocean plankton started, that's when the carbon dioxide levels came down even further.
Yeah, so tell us about that little bit of the cycle then. Why is it that the ocean plankton should be changing the carbon dioxide levels?
Well, the ocean plankton, or at least some of it, is fixing carbon dioxide. And we have to remember that probably 30% of the carbon dioxide produced today, around about 30%, is being soaked up by the oceans. And that's creating, on one hand, ocean acidification, but also it's making carbonate available within the oceans. And therefore, James Lovelock's idea of a Gaia hypothesis, while I don't believe in the complete Gaia hypothesis, a lot of it is true that animals and plants are controlling our climate. But actually the oceanic plankton is creating more oxygen and removing more carbon dioxide than your rainforests.
Is it something like every 1 in every 3 breaths or something comes from oceans? That's one of the things. I'm not sure if that's entirely true.
It's something like that, and we could argue the details, but it really is important to get the picture that the ocean health is as important as the tropical forest health.
I'd like to bring in Jenny here in the sense of, because I mean, when I went through geology in the 1980s, and all that Gaia stuff was heresy, complete heresy. All just hated it. But then again, they hated everything else. They hated asteroid impacts. They hated plate tectonics when it came along and all that. So we are quite a conservative bunch, but we really hated Gaia. But it seems to me now that every geology course in the land is now teaching Earth system science, our branding, and it is this interconnected.
I was teaching it for the Open University, so yes.
So how do you feel about that transition? It's interesting. In some ways, both of you gone through that change to this interconnected, where suddenly you can't just talk about the solid crust or the atmosphere. You have to talk about all of the interconnections.
I think it's fascinating. And actually, talking about plants and animals affecting the atmosphere, well, we're basically animals, aren't we? And look at what we're doing. It's exactly the same thing. But it is very interesting, and I've been talking to other people about the effect of weathering and vegetation, and the fact that vegetation has on erosion. I mean, it's so interlocking, the whole thing. Most of my research has been on rivers, and it's key to that, whether or not you've got vegetation upstream. It's really.
I remember hearing, this is me digressing. I remember reading that, when plants first come along, that's when you get the alluvial river, the meandering river, because you fix the soil essentially in place, which is
Yes, Martin Gibling in Canada has written quite a lot about that, and some really keynote stuff. It's good.
So as we go through, that transformation, as we come out of the red continent period, the Pangea, when we have all the land masses together and we get that kind of classic kind of red rocks, as we pass through that, we go into a very different planetary environment. Malcolm, do you want to pick up the story there and tell us what's happening to the planet at that time?
Well, yes, I mean, the red rock incident is obviously very important in a sense that when we look at the water on the planet as distinct from the atmosphere, the water content of the Earth has probably stabilized for a long time now. And what we're doing is moving it around. And we move it around by changing the shape of the ocean basins. But in particular, we move it around by having ice, the cryosphere. And the balance of the hydrosphere and the cryosphere is very important. So in that red rocks period, not only were the continents all together, which created a rather peculiar plate tectonic situation, but we had a southern hemisphere glaciation, and sea level fell quite a markedly amount to, 150 meters down on normal. And therefore, the continental area that those red rocks were formed in, we talk about them as terrestrial. Well, yes, they were, because sea level, because of the amount of ice on the planet, sea level was low. And the whole of Pangea virtually was a terrestrial environment. So when we look at the English Riviera, what we see are continental deposits. And there was virtually no water between us and Scandinavia. The only water there was inland lakes that were hypersaline lakes in the North Sea basin. And of course, those evaporitic basins control North Sea gas and the oil fields and the gas fields of the North Sea basin. So they're economically very important. But they're all down to the fact that the cryosphere, the volume of ice was high. That reduced sea level quite dramatically. And we end up with all these nice terrestrial deposits. And having had the benefit of working in parts of the world like the Oman, and driving around all the wadis there, and you see those rocks, but then you look at them and think, hang on, these rocks in Oman, they're not red. And of course, they aren't red because they only become red when they're buried, and water, groundwater that was still there, actually converts the iron minerals to the iron oxides, and they turned red in depth.
I'd never thought about that. So that redness can happen, what, tens of millions of years later? I mean, when do you think the redness would have occurred then?
Well, when you dig holes in the Oman, you probably have to go back 3, 4, 5 million years to actually see the red coloration forming. And that's interesting because the red rocks are such a characteristic feature of Torbay. And it's very difficult to get over to people that, you know, when those rocks were forming, they weren't red. I've seen some wonderful dioramas, and not only were the rocks red, but the sky was red, everything was red. And you're thinking, hang on, this isn't the Earth that I know.
That's interesting because it's such an iconic part of that landscape, that red landscape. But let's skip forward then, because we're going to leave that red continent behind. We're going to break up Pangaea. Tell us about that breakup and then what that did as we go into that Jurassic period that then kind of followed.
Well, when we began to move out of that, and we went through the Triassic, which we can see in East Devon, and you can see from Babbacombe Downs if you look across the bay. As we began to split Pangaea apart, ocean crust formation was displacing water because it was actually expanding the ocean ridges.
Maybe worthwhile saying, we're about 200 million years at this point, yeah, with that breakup starts at least.
Yes, and of course, by that time, once the continent Pangaea had begun to fragment, then the Ice Age ended, so that water melted. So coupled with the melting of the Permian Ice Age and the growth of ocean ridges, sea level rose. And gradually through time, as you move from the Triassic into the Jurassic, we can see that becoming marine. And of course, one of the biggest arguing points is where's the Triassic-Jurassic boundary based on ammonites and things like that. And of course, if you're in a transition from continental deposits to marine deposits, using marine fossils as a time scale becomes very, very difficult because it depends on where sea level is rather than time scales. But of course, when you get into the Jurassic, we've got to think of Southwest England not as connected to everywhere. Southwest England was an island because there was Jurassic deposits in the English Channel, there's Jurassic deposits to the east, there's Jurassic in the Bristol Channel, and it's out to the far southwest. So Cornwall and Devon was an island. Now, whether or not there were dinosaurs running around on it, because it would depend on whether they could get there or not. They're notoriously not good swimmers.
This is going to feed the Cornish Devon independence movement no end to realise that we actually were a self-contained island with marine conditions all around. I never. Did you reckon there were dinosaurs kind of running around here? There must have been, I guess. Do you think?
Well, I'm sure Mike Benton would love there be dinosaurs, but we've actually got no fossil evidence of that at all. What we find in particularly if you go to Lyme Regis, is we do find fossil wood quite frequently. And that's obviously washed off these island areas. But I'm sure the Southwest was virtually an island. And the granite was beginning to weather because you get kaolinite and other minerals from the granite. And so we can actually think of it as an island. But then as you go through the Jurassic time, continental configuration meant that sea level actually fell again, connecting the Southwest to Britain and Wales and Scotland. And then as you move into the Cretaceous, sea level rose again, because particularly in the middle of the Cretaceous, that was the fastest seafloor spreading that we've ever recorded. And the present continents all just moved apart. Sea level rose dramatically. And it's very difficult to communicate with people when they look at Dartmoor, that at certain points in time, Dartmoor was under the sea. You know, it's counterintuitive to think that the chalk cliffs of East Devon, actually, there was chalk on top of Dartmoor.
Really?
And I always remember taking one group out to beer, and they said, well, what's the paleo temperature of the chalk sea? And I said, well, about 26, 27 degrees centigrade. And the immediate reaction was, oh, that would be wonderful and warm and lovely. I said, yeah, wonderful and warm, but the downside is sea level's 200 meters up there.
Yeah.
And the nearest shoreline to Devon was southern Sweden.
See, I want to bring,
that's the scale of it.
Yeah, I want to bring Jenny in here, because this is, as a geologist, this is one of these things it's kind of hard to explain to people, but we have to keep these parallel worlds in our head. The world that we're looking at, even though we're staring at a cliff of whatever rock it is taking us to this very different place. And I mean, I guess for you, that's one of the attractions of geology itself.
Well, yes, it's four-dimensional chess as an exercise of mental agility.
Jenny, what do you think on that?
I think it's true, and I've worked a lot with physical geographers, and it's noticeable that some of them have more difficulty with ideas of deep time, to call it that. You know, talking about the Quaternary, I'll be talking about thousands of years, and then you're looking at the bedrock underneath it, and you're suddenly flipping and talking about millions of years. But you're still dealing with the same processes, and it's the thing about trying to look at the place you're logging or whatever, and trying to interpret how it would have been and how it might have got to be like that. And that for me is one of the really exciting things about geology. I think it's fantastic.
The other thing that strikes me is that you kind of realise when you talk to ordinary people, and I say that very deliberately, normal people, not geologists, is that they're transfixed, they're locked into the landscape that's around them. And so I've been in lots of them where I've been explaining something about the landscape, and they're just quizzically looking at me, and they would say, what do you mean, if you eroded those cliffs, how do you know what's behind them? You know, if you've got flat layers, or you assume the same layers, how do you know? You know, this, they see this kind of as an artifice, really, rather than the way that kind of geologists see it. And so I guess so much is from that reading the rocks. Picking up the same, we're in the Cretaceous, so how many million years ago, to help the listener? I mean,
well, the chalk was formed between about 100 million years ago and 65 million years ago, when we enter the Cenozoic. And of course, we don't anywhere see any evidence of this in the English Riviera Geopark. But of course, when we look at things like the beach at Slapton Sands, well, sands is the wrong word because it's coarse pebbles, But when we look at that beach, about 80% of it is flints, cherts, that have been washed up from the English Channel. There's hardly any indigenous local rocks in there.
Right.
And all these flints and cherts have come from the Cretaceous. So when we're looking at the geopark, what we're looking at is evidence that at one time it was below the sea, at one time it was buried in chalk. And of course, where's all the chalk gone? It's been removed. Now, to geologists with the timescales we work on, we quite happily expect that things are eroding away, being transported. But it's a very difficult concept for people to actually grasp, that no evidence allows you, and I use the word allows you, to make interpretations of what was going on when you've got no evidence. But that's part of what geology does, that you look at something and you're always thinking of what's missing rather than what's actually in front of you. And that's a turnaround situation to most people.
And go back to the chalk. The chalk is pretty critical for changing the climate. So you've got this huge thickness of these. Well, talk us through what the chalk is made of and its importance for climate.
Well, the chalk is really strange in a sense that when you stand on a beach looking at a chalk cliff, and as you say, you can have 1,200, 1,400 meters of the stuff. When you realize that 90% of the chalk is made up of things that you literally can put hundreds, if not thousands, on a pinhead. I mean, the average particle size in the chalk is 0.002 of a millimeter. These coccoliths, these marine algae, and therefore when you want to look at what the chalk's made of, a hand lens that we use in the field doesn't help much. A normal microscope doesn't help much. You need a scanning electron microscope to see those particles. But when you think of all that fixed calcium carbonate, we think that the chalk sea was formed in an atmosphere where perhaps it was 8 or 12 times the present level of carbon dioxide in the atmosphere. And the only reason you can form the chalk is that the carbonate saturation in the water was so high that it counteracted what would have been ocean acidification with that level of carbon dioxide. And so the whole of the chalk succession is just magnificent as a record, and we can look at the evolution of groups of fossils, because in most of the geological record where we look at evolution, it's full of gaps and jumps, and it's very difficult to piece together progressive evolution. But the chalk, you can do it because the environment didn't change for maybe 25, 30 million years. And therefore you see progressive evolution. And of course, if you didn't do that, I wouldn't have been able to do the survey work for the Channel Tunnel or the Thames Barrier or anything like that, because you rely on those evolutionary changes to work out the stratigraphy. But the chalk's fascinating, absolutely fascinating, because nowhere else in the geological record do we have such a continual long period of time of one uniform. I know it's not uniform, it's a lot of variation, but to the average look, it seems pretty uniform.
Looks uniform to me as a structural geologist, I have to say.
And of course it's marine. So a long period of marine deposition, it is continuous, and that's absolutely brilliant. That's not the case in the Quaternary.
No, I'm going to get to, I'm Jenny going to get tomorrow to the Quaternary. We're rapidly going downhill in terms of climate there. And of course, that Cretaceous, that chalk sea wasn't just the UK. I mean, it was right across Europe. It's an extraordinary period and beyond. So that's a greenhouse climate, Malcolm. Yeah, that's a warm, no ice on either pole.
Now that's the interesting debate as to whether or not there was ice somewhere on the planet, maybe a small amount. And there's a book being published literally just earlier this year, questioning what was controlling these changes in sea level, because some people think it was groundwater. Well, personally, I don't think there's that much groundwater to have that effect. The ocean basins weren't changing that much in terms of shape. And therefore, was there ice? Was there a small ice cap in the Antarctic? And certainly, when I look at some of the ocean plankton within the chalk, I can see migrations northwards or southwards, and then contracting again, northwards, southwards, contracting. And it almost seems as if there is a climate signal that implies small glacial centers, probably just on West Antarctica. Because because we know that the real glaciation began in the Cenozoic. I mean, it's been so dated as 32 million years ago, so precisely with deep sea drilling cores. But we know that the Antarctic ice sheet really began properly in the mid-Cenozoic, around about the Eocene-Oligocene boundary. And then the Arctic ice sheet didn't start forming till about 3.5 million years ago. So it was well behind the Antarctic.
So if we can step back a little bit, Jenny, what is it that we had that greenhouse state, if you like, in Cretaceous, and then we have this, during the third phase of Earth history, the Cenozoic, we've got this global cooling, a kind of relatively steady decline in kind of temperatures. What was driving that, kind of pushing us gradually till this point, 32, when we suddenly get ice picking up in the Antarctic?
Well, I reckon it's a mixture of things. It depends on where the continents are, and if you've got land at the poles, that will encourage ice to form. And ice on land takes more water out of the oceans than ice on sea ice. But the control on it is thought probably to be solar radiation and the cycles of radiation reaching various parts of the planet. They were sorted out by a Serbian called Milankovic, although there was a Scot called Kroll who shouldn't be forgotten.
Kroll. James
I like
Kroll.
Yeah. Absolutely.
Yes.
Yes, I'd forgotten the Scottish connection there. That was a good one, yeah.
That's why I'd throw that in.
Yeah, but it's the Earth's route around the sun is not the same all the time, and there are three main cycles. Do you want me to go into them?
No. Well, I was just thinking, it's a gradual planetary cooling that happens, and we see these cycles as you were mentioning. But the big
which sits on top of that.
Exactly. So it's kind of these set of nested rhythms. But the overall direction of travel is cooling over that kind of last period.
Yeah.
I feel kind of bad because I'm jumping over the most momentous event, which is 65 million years ago, the end of the dinosaurs, all the things at the end of the Cretaceous. But just very quickly, Malcolm, we don't see any evidence of that kind of time period, that incident in the southwest, do we?
No, we don't have a boundary succession. We see the change in terms of the paleontology between proven Cretaceous and the lower part of the Cenozoic. But I mean, we don't actually have physically any evidence that we can point to. The nearest location is in the Netherlands and in the North Sea Basin. And there we see some very strange deposits which are well away from the impact event of Chicxulub in Mexico. And of course, the big debate is just how much did the Deccan volcanics in India have compared to the impact. Now, I've paddled up all the rivers in parts of Texas, looking at the impact event and the tidal waves, and quite clearly that was what triggered the event. You can time things to recovery from that impact event and the tsunami. You can measure the timescale by using our friend Milankovitch cycles, and you can show that there are about 6 climate cycles to recovery. So we're looking in terms of life recovering from the dinosaur and ammonite extinction within 80,000 years.
Yeah,
really a very fast turnaround.
So, I mean, I don't want to get into it too much because it's not something we necessarily see. What is quite interesting, I think, is we would definitely have got that tsunami wave. So if the things in Mexico impact and you get evidence of it in Denmark and the North Sea, we would definitely have flooded past us. But unfortunately, no legacy. I'm interested in suddenly the ice. We get to about 35 million years, 32 million years, we suddenly get significant ice developing in Antarctica, and then gradually that really it staggers us into a set of ice ages. Now, when I went through university, there were only 5 ice ages, and there's now hundreds of them. So, Jenny, talk us through our understanding of the ice ages has been completely transformed in the last few decades.
Yes, and it's been transformed. Really, is why I was talking about the marine record previously. It's by ocean drilling and looking at relationships of a cold signal and a warm signal in those cores, and a picture's been built up of these sort of alternations between cold and warm periods, and it's in a way we've got a huge amount of data that's very detailed, so we know a lot about a much shorter period of time. So you've got much more sorry, I'm becoming incoherent. Much more detail about sort of shifts between cold and warm, and they're thought to have been about 12 cycles in the last 80,000 years, so that's quite a lot. It's quite difficult though to plot these things on terrestrial deposits. It's because the record isn't continuous, hence my point earlier on. But what people are trying to do is to match the terrestrial record with that marine curve. But quaternary scientists use all sorts of different records to try and match against the marine oxygen isotope curve. And staggeringly, a lot of them do match. There's a very good set of data from China, from the Loess Plateau, where the loess alternates with soil. And the loess forms in cold, dry periods, and the soil forms in warm, wet periods. And the patterns and the dating matches with the marine curve pretty well. So that's the sort of backbone that we've got for the timescale. And then basically what we're trying to do is to hook things on that. So there are people who get really uptight about the fact that we're using a marine curve to try and set up a stratigraphy for terrestrial deposits. My old supervisor, Phil Gibbard, gets extremely uptight about this. And if you light blue touch paper, so I always have to remember to call them marine oxygen isotope stages. But what we've got in Torbay, of course, is we've got evidence of changes in sea level. If you've got these shifts in climate, when it's very cold, there's more ice. So when there's more ice, there's less water in the ocean, so sea level falls. If it's very warm, there's more water in the oceans, so higher sea level, and hence the raised beaches. We get these, so there are these oscillations in sea level which are related to changes in climate. And sea level change is interesting because it can be caused, if you're looking at one particular locality, there's several things could cause it. It may be something local, your land might be moving, or it could be something global where the sea is moving. And that's why it's very important to just not take one site, but to sort of look further around. And it's interesting in Devon because not only are there raised beaches, those are abandoned higher up beaches in Torbay, they've also got them on the North Devon coast. So the evidence is all stacking up for the fact this is a global signal of sea level change.
So how many of these raised shorelines do we have in the southwest? How many of those climate fluctuations, those high stands, sea level high stands?
Well, that's a $25,000 question, and there have been huge arguments about it over the past. There were past workers used to refer to different. There was a 250-foot level. There was a lot of work done on trying to match things purely by altitude, which is, you have to be a little bit careful about that, because there will be changes as you go across the landscape. There are certainly, there are at least 2 very clear levels of raised beaches. Part of the difficulty as well, of course, is that if you get a higher stand of sea level, it's going to obliterate some of the earlier evidence. So we're pretty sure that we've got some more recent levels. I mean, Hope's Nose is a fantastic example. We were talking about that earlier when we were chatting, where you've got a wonderful raised beach, which is some 15 meters above present sea level. If you look at it, it's got oysters and things like that in it. And it looks just like a present beach, and it's about 3 meters thick, and perhaps a bit more than that, but it's way up. So how did that happen? And that's fascinated scientists and amateur naturalists for years. There's another beach on the seaward side of Thatcher Rock, which is slightly lower than the one at Hope's Nose, but that's got a lot of shells in it, and those have been investigated over a long period of time to see whether they represent cold or warm weather environments. There are a lot of warm weather things there, which is interesting. I think Matt Telfer at Plymouth is starting to do some more work on trying to date these sediments, which will be really interesting, because we've always...
No, finish, please.
So we've always assumed that they were probably from the last warm period, which would be about 125,000 years ago. Yeah. But it's possible they were from the one before that. And I
was just thinking how things go in and out of fashion.
Yeah, oh, absolutely.
Suddenly, you know, those raised beaches of the southwest where lots of people kind of study. I remember Anthony Orme and people like that.
Oh, Anthony Orme, yes.
But and then they've gone out and been and then suddenly, and maybe the contemporary discussion around climate change and getting data has brought it back in. But maybe I think for the listener, it might be useful to think about to paint some kind of picture of Ice Age Britain. So, my basic knowledge, ice never came as far south as Torre Bay. Is that right? Yeah. Well, tell me I'm wrong. I'm really happy.
There's certainly evidence for ice coming as far as the north coast of Devon, and there are deposits around Fremington, which there've been a huge arguments about it. It was thought possibly to have been an ice-dammed lake, or possibly to have been just the ice up against the cliffs or stopping drainage of rivers. Then there was another set of theories who thought that the Fremington clays were actually glacial. And I think most people now think that it's just an ice-dammed lake because there's lots of layers in it, so that would work. There is some fairly recent work on Lundy, where workers have found what they're interpreting as striations on the granite on Lundy, and they've also identified some glacial till, which is the material from underneath the glacier. So that's still really argued about, and there's big dispute at the moment about whether or not there was an ice cap on Dartmoor, and that's Stephen Harrison's work from.
That's interesting. So what time period are we talking about for those? Is that the last glacial maximum? The last time the ice was at its fullest extent? Are we talking in that period?
No. Well, that's sorry, two different things. It wasn't the last glaciation, which was the Devonsian, confusingly very similar to the Devonian, but it's a Devonsian with 2 E's. Not that period, but probably the one before, or the one before that, the Anglian.
I'm just curious, I'm trying to think about the last glacial maximum. So 30,000 to about 18,000. It's kind of, if in this area, what would it have been like? And how far north would you have had to go to finally see the ice, in front of the ice extent? So
you'd probably have had to have gone to Wales or up towards Bristol, around there. It would have been jolly cold here. It would have been periglacial, so ground would have frozen during the winters. it would have been very dry because of water being locked up in ice caps elsewhere. So the bedrock would have been available to be eroded. So there would have been a lot of sediment deposition going on as well. It wouldn't have been a terribly nice place to be. Things like the rivers, the Exe Valley, that we now think that the whole of that valley was actually a braided river because of the amount of sediment that we're finding that's been moved across. Very little evidence of human habitation during that period. Just a few bits and pieces later on, probably because it wasn't very pleasant. You know, it was a large braided river that was sort of not very nice in the winters. So
we've got people in the area though. We've got humans. You know. So,
let me see, how far back are we?
Well, I just think that last certainly about what 30,000 or so for good humans.
Well, it's really important to link in the record that we see, and I'm used to talking about marine isotope stages, but when you come to the southwest, around the headlands like Hope's Nose or Berry Head, there are submarine cliff lines which represent eroded levels offshore.
Yes.
And then in particular, some work that Chris Proctor's done, and I'm supposed to be doing because the samples are sitting in my lockdown office in Plymouth.
We need you to do it, Malcolm.
Yeah. There are marine caves.
They're analysing.
Yeah, but there are marine caves around Tor Bay.
Right.
And these marine caves are really quite important because when you look at the succession in those caves, it's an intermittent record of marine sedimentation, speleothems, marine sedimentation, etc. And these sea level cycles you can see within those sediments. But of course, those marine caves that we see on Berry Head and the related areas, we then have to jump to the other caves like the Buckfast Caves or Kent's Cavern or the caves up near Chudley that actually have the terrestrial record. And so we've got cave systems in the southwest which show both a marine record and a terrestrial record. And we must be one of the few places where that happens.
Yeah.
So yeah, just to be clear for the listeners, so if we're going back to that last maximum glaciation, sea level is way 100, 150 meters or so lower than. So there's a whole expansive landscape there where fluctuations in sea level would have been, as you say, creating caves, drowning caves, creating caves, and then exposing them. So it is extraordinary that. I mean, how much do we really know about that offshore realm? It must be very hard to get information.
There's not too much. Malcolm, I think you know more than I do, but there was some sonar done, wasn't there? With most of it was round by the Solent, and you can see where the Solent River comes round the Isle of Wight and then out again, and there's a channel there. And the Exe and the team join up offshore, but Malcolm, you're much more into the marine stuff.
Well, yes, I know it's not the English Riviera Geopark, but if you go and stand on Plymouth Hoe and watch the Brittany Ferries boat, it follows the old channel of the River Tamar when sea level was much lower. That's why there's that rather strange meandering route out of Plymouth Sound. But I mean, there are places in the southwest where we do see a record. Around the Scilly Isles, around the Scillies, James Scourse has got a lot of evidence of sea ice washing into there. If you go to the Channel Islands, offshore Jersey, you can see the record, which is a beautiful record going from almost a forest vegetation being drowned by sea level rise over the last 9,000 years following the last glacial maximum. And of course, these modern climate changes are just part of that story. But I mean, I know Phil Gibbard really can't stand marine isotope records, but let's be honest, there's two things that have given us this wonderfully accurate timescale for these sea level and climate cycles. One is deep sea drilling cores, where we can measure stable isotopes and we can see all the changes. We can see changes in ocean acidification caused by fluctuations in carbon dioxide within those cores. But the other thing we can see is, of course, that those marine cores in modern environments, like the Caribbean or offshore Atlantic, when you go to the Antarctic or Greenland and drill ice cores, you can actually look at the gas bubbles in those ice cores and see that these climate cycles relate to carbon dioxide, because you can measure the carbon dioxide. Now, when you measure that carbon dioxide, the maximum level of carbon dioxide in the atmosphere is about 360 parts per million. When you look at the modern day, we're up to 420. And that is the one proof that we are now into territory created by human activity. But I mean, we can actually see evidence of some of these changes in the atmosphere and sea level when you stand in the Geopark.
Well, can we hold that thought? Because I'd like to bring it up to that contemporary, but very much in just a second. Can we, as we come out of the Ice Age, we get that rapid rise in sea level. And what do we see, Jenny, in the Torbay area as a result of that rising sea level?
Well, probably the most obvious thing is at Goodrington, where there's a drowned forest, which you can see when if there's a particularly low tide, and if there isn't too much sand on the beach, that's beautifully exposed. There was some work done on that about 10 years or so ago, and it's been dated to have been probably 9,000 years old, Mesolithic, and there's evidence of people being there then. So certainly I used to take students a lot to Goodrington, and they used to find it quite bewildering, because you would see the drowned forest, you go a bit further round and there's a wonderful unconformity where you've got the Permian and the Carboniferous sort of doing that. So it's obviously something very odd has happened on, and it's this thing about time and length of time for things to happen. But to have a drowned forest and a raised beach, and there's one at Shoalstone, which is not too far from Goodrington, reasonably close to each other, is quite confusing for people trying to work out what's going on in this period. So, and trying to put a peg on them to say how old some of these things are is quite useful. Well, Malcolm's right that the marine oxygen isotope curve is a really useful peg. It's a skeleton, isn't it? So you hook on what's happening when. But certainly that Goodrington drowned forest is the most obvious thing I can think of. We've got some spectacular raised beaches in Torbay, which will show us when sea level was higher. But I think that's probably the best one, yeah.
We have this kind of rising sea level that comes after the ice, and then that kind of wanes as that global meltwater kind of balances itself out, really. Which is why I really like to kind of bring it right up to the present day with climate change, because quite a lot of people use geology and use past climate as a kind of stick to beat contemporary climate change with. They say, oh, the parts per million CO2, you know, even going back a few 100 million years isn't that high, and sea level has been up and down and all the rest of it. What's your take on that in terms of what does the past climate tell us about the present climate? Jenny, do you want to start us off on that?
I think what's interesting is, as you say, people often will comment that temperatures 125,000 years ago were a lot warmer than they are now. CO2 has certainly been all over the place. It doesn't suit us as a species, and I think that's the key thing. And certainly the amount of CO2 and other greenhouse gases that humans are putting into the atmosphere is disrupting some of the natural systems. we probably should be on the long, slow decline towards another cold period at the moment, but that's not happening because of what's going on in the atmosphere. So yeah, really interesting. But how you deal with climate change deniers is rather more tricky. I think there are records that you can show people. The records from Hawaii of the amount of CO2 in the atmosphere is really important. And that I notice now that's reported daily in The Guardian, which is quite interesting. Yeah. So it's important enough for that to happen. But yeah.
Malcolm, you've alluded to this several times in the interview about, you know, past changes, in a way, geologically dwarfing some of the ones we have today. You know, go back to the really earliest times, we get records, thousands of parts per million. But you know, there's no getting away from the fact that there's something different about these changes now than they have been in the geological past. Would you agree?
Well, yes, and speaking to an ardent fellow from north of the border, I've got a Scottish heritage too, but I mean, James Hutton famously said, the present is the key to the past in interpreting geology. But I mean, a lot of geologists, aside from kicking occasionally the climate change people, do actually genuinely believe that the past is the key to the future, that we actually understand the physical processes. And, you know, if you stand on Berry Head and look across Tor Bay, all those hilltops behind Torquay are at the same height. And that is the last time we had this sort of present level of carbon dioxide in the atmosphere, where you're into the middle Pliocene. And that is a marine surface. And buried in that marine surface, there's an earlier one from the middle Miocene. So just by standing on Berry Head, you can actually appreciate these changes. And I think the important thing for those trying to understand what's happening as carbon dioxide is getting into the atmosphere, we can measure ocean acidification absolutely precisely, because microfossil people look at the thickness of the shells of plankton. We're looking at the corrosion within pelagic gastropods, and we can see the effects through time on the plankton. And therefore, it's bringing it into the biology as well. But of course, the one thing that we're really struggling with is that no matter how well people behave in terms of reducing carbon dioxide emissions, there are two problems that we really can't address. And they're almost nobody's fault. First of all are these marine gas deposits under the ocean, which are becoming unstable because the ocean temperatures are rising. And if they release clouds of methane into the atmosphere, that will have a pretty bad effect. But I mean, the worst one is if you look at the weather reports just last week,
Siberia.
Russia in Siberia has had 2 to 3 weeks of temperatures at 38 degrees centigrade. Now, what's that doing to the permafrost?
Yeah.
And it's not the Russians' fault. I mean, don't blame the Russians for that, and don't blame the Canadians for that, because it's global climate which is creating that loss of the permafrost. And if there ever was a thing that you can attribute to humans, it's that.
Yeah, it's all intensifying, isn't it? And more hurricanes, more typhoons. It's all the same thing. It's all intensifying. Warm seawater will do that.
Sorry to cut a question. I was just one of the things I was often thinking is when we try and talk climate change, and you alluded to it in the way you describe it there. There's all these complexities in the system. You know, sometimes you get it means more rainfall here and less rainfall there, and people think both ways. increased storminess and things. And a lot of it's really complicated. But it always struck me that the ocean acidification is actually quite a simple concept that geologically we've got a good handle on, and it's absolutely terrifying in the sense of being a potentially existential threat. Malcolm, do you want to take us through? I mean, the idea of those warming oceans and that lowering of the ability of organisms to build their shells from calcium carbonate, the potential loss of the reef system, seems to be something that all the global food stocks kind of rely on. And you kind of alluded to, again, you mentioned something, things being locked in. That, to my mind, seems locked into the system. How do you see ocean acidification? Let's finish on that thought.
Well, there's two aspects of it, if you'll forgive me. I mean, one aspect is that warmer oceans hold less oxygen, dissolved oxygen, and therefore the increasing temperature of the oceans means that those animals that rely on oxygen are going to find it more and more difficult. Those organisms that rely, the plankton, those pelagic gastropods that literally are struggling to create their calcium carbonate shells, they're a food stock for most of the world's fisheries. Now, can these organisms live without a shell? Probably. Would they still be a food source? Well, yes, I imagine that's the case. But of course, we really don't, we're in uncharted territory here of trying to understand the biology of organisms. And I mean, the UK is doing a wonderful job, along with colleagues in other parts of Europe. These traverses down the Atlantic Ocean looking at the plankton, that happens every 2 or 3 years. And there's now a tremendous database to show how these organisms are being affected, even in very short timescales. But of course, it's really interesting, and one of the joys of Tor Bay is that we often forget that Tor Bay has got marine conservation zones, or a marine conservation zone, and round Tor Bay there's these wonderful seagrass meadows. Yeah. Now those seagrass meadows, what we've done is we've found a seagrass meadow in the chalk. And that's an interesting thing, that it pushes the evolution of seagrass back 50 million years. But also it means that they seem to respond to increased carbon dioxide. So seagrass are going to grow more and more because of the carbon dioxide. But down in Cornwall, we have these wonderful calcareous seaweeds, known affectionately as merle. And they are, of course, relying on calcium carbonate, and they're dissolving. And so we've got a wonderful balancing act between seagrass meadows, good thing, seahorses love it, and the merle, which other things like, which is beginning to fragment and fall apart. So complex ecosystems are very difficult to understand, but certainly areas like Tor Bay are up there with providing information. And, you know, the Geopark really doesn't just end at the coastline. I'm putting in a bid for the marine environment as well.
Absolutely, yeah.
That's great. No, I'm all for that. Well, let's just kind of final thoughts then. I mean, I'm interested in your kind of view of, you know, standing somewhere in that Tor Bay area and looking out. You know, what is it that resonates with you about Tor Bay? I mean, Malcolm, and then I'll go to Jenny. Malcolm, what gets you when you sit and stand and stare at that landscape?
I suppose the main thing for me is that if you can piece together that history when you look out over Tor Bay, and of course it tries to confuse you because the Devonian rocks around the southern part of Tor Bay are actually red. Not
Yes.
because they were red, they just got stained by the stuff on top. So of course that creates a problem. I always remember talking to a couple who were on holiday, and they'd been told by their hotel that there were volcanic rocks in Torbay. And of course that's partly true. And they put their hand on a rock and said, well, it's still warm. And I'm standing there looking at them thinking, well, yeah, the sun's up there and that's why they're warm. But of course, there are volcanic rocks in Torbay. And it's interesting that those reefal limestones that Kevin was talking about in the Devonian, what we can see there is the impact of volcanic ashes. And you know, you've got beds of coral overlain by volcanic ash, which literally killed them.
Yeah.
And so there's all sorts of things like
those
that.
narratives then, is that, you know, from that landscape, you're drawing out those sometimes quite minutiae stories of
yeah. But it's piecing all that together and trying, if you go on a boat cruise around Torbay, you can bring an awful lot of that out to people if you can explain it in words that are understandable.
I have a vision of the Malcolm Hart boat trips kind of thing coming up there. Jenny,
I've been on one. It was excellent. It was
what for you the kind of the resonance when you're looking out over the Torbay area in terms of that viewing the past, the geological?
Yeah, well, I think it's fascinating because there are so many places where you can see evidence of very different environments. I used to take students a lot to the Goodwin area, and it's fabulous there because you can see structures, you can see different rock types, you can see different climatic regimes, all sorts of things. It's just wonderful. And I mean, Hope's Nose Raised Beach is just spectacular. There's nothing else like it. I took a colleague from the Open University there once, and I just said, there's quite a nice raised beach down here, you might like it. So we went down there and she stood on it and she said nothing. And I thought, oh, she didn't like it. And she turned around and she said, Jenny, this is a spectacular raised beach. It's not a rather nice raised beach. So I think we should celebrate it. And just to look across to Thatcher Rock and to think, yes, there's something else there as well, and which might link in with that. And we've become quite interested in the history of Torbay and the amateur naturalists there. And so many people had become intrigued by those raised beaches. I mean, Jukes Brown, who's a big name in past geology. There was a local guy called Hunt, Malcolm and I have chuckles about because there were some fairly interesting disputes with the professionals in London. He also became heavily involved in Thatcher Rock and collected a lot of shells there to get them analysed to see what sort of climate they were laid down in. And there's plenty to do. There's loads more to do. So we want Malcolm to get analysing those specimens and add to the story.
Great that it's kind of never stopped drawing out those questions, that curiosity. This incredible landscape.
And Chris Proctor's work on the caves is really important, linking the terrestrial and the marine. Really important work. Yeah.
And I know that you're both active in the Devonshire Association. Do you want to say a quick word about that? Something that people might be interested in involved with.
It's a long-standing organisation. We're over 150, isn't it, Malcolm? Over 150 years old. Malcolm edits our translation.
Well, it was 1862 when William Pengelly founded it, or helped to found it. And
he was a talking man.
He was a classic amateur in the sense of many other amateurs in the British Isles. And the geosciences have got a wonderful track record of amateur involvement. I mean, you know, Curry's, I'm not advertising, but Curry's PC World. I mean, Dennis Curry was a fantastic paleontologist.
Yeah.
In his spare time.
He started Curry's thing, is it?
Yeah.
And the Curry Fund from the GA, So,
And I mean, it was William Pengelly who was involved with the Devonshire Association, but he also founded the Torquay Natural History Society. He helped found the Torquay Natural History Museum, and he designed the methodology of cave exploration, which, okay, it's been modified, but you know,
important.
he should get the credit for having designed that system. And he was a school teacher. He wasn't a professional geologist.
And as a geology section, we're really proud that it was geologists who actually started the Devonshire Association. We think that's great. So the present day, we still run a section. At the moment, it's a bit tricky with the virus, but we run field trips and we have lectures several times a year. And we're a really nice mix of amateurs and professionals, which is, I think, really important. I think anybody can enjoy geology. It just makes you look at the landscape a bit differently. And I think there's a huge amount to be gained from that. And it's just so interesting.
Well, I think you've just sold it extremely well to me today. If anyone is interested, I'm sure you'd be delighted to if they get in touch with you. But for now, thank you, Malcolm. Thank you, Jenny, for taking us through sea level change and climate change over a couple 100 million years in just short of an hour. Thank you very much.
Not bad. Thanks.